This section is limits at infinity, which is end behavior, which is horizontal asymptotes. You did these in college algebra. When they asked you about end behavior in college algebra, instead of limit notation, you did as x approaches infinity, the function approaches whatever it's approaching. Do y'all remember that?
Yeah.
If you took college algebra here, that's the notation they should have used if they used Webster. Okay, well that's just a form of writing it in limit notation. And as x goes to infinity, what we're looking for is horizontal asymptotes. Now, it doesn't always go to a horizontal asymptote, right? A horizontal asymptote is a horizontal line that's a finite y value that it's approaching. But think about a parabola. Does a parabola have a horizontal asymptote? No. So if we look at the limit as x goes to positive or negative infinity of a parabola, we're going to get infinite limits. But when it approaches a finite value, we get a horizontal asymptote. Vertical asymptotes are x equals something. Horizontal asymptotes are y equals something. Right? So if I pick some value of y and my curve is approaching it, that's a horizontal line. Y equals a number. Vertical lines are x equals something. Now, for a horizontal asymptote, we're looking at as it goes to positive infinity or negative infinity. Notice as this little sketch I drew goes to negative infinity, there is no horizontal asymptote. It's only in the positive direction. When you're checking for horizontal asymptotes, you need to check both x going to infinity and x going to negative infinity, because you might get a horizontal asymptote in one direction or the other, or two different ones, or one that matches up for both behaviors. Okay, so find the limit if possible, meaning these aren't all going to result in horizontal asymptotes. Some of them, their end behavior is going to go to positive or negative infinity. So what I'm going to do is a direct substitution. Okay, so let's think about the second term here. If I have 2 pizzas and I have to feed 1 million people, how much pizza does everybody get?
Crumb. Yeah.
Not even, right? A non-visible crumb. That behavior is approaching 0. When you get a number over infinity or negative infinity, we're going to say that's 0. Okay, so a number over 0, we get positive or negative infinity. But a number over positive or negative infinity, we get 0. Yeah?
Were you supposed to change the sign from the limit to...
Good catch. Doesn't matter though, does it?
Yes.
Because I'm subtracting 0 and adding 0. It doesn't matter. But yes, on the test, I would ding you for it. So it does matter. Okay, so we're going to say anytime we see a number over infinity, it's going to go to 0. So this limit is just equal to 5. And when you do these, don't get so focused on the infinity term that you forget about the other one. When I put something like this on a test, there's usually somebody who will tell me the answer is 0 because they forget about that 5. But 5 would only be insignificant if we were comparing it to infinity. Compared to 0, it's 5. Okay? We're going to do direct substitution on this one as well. 3 over e to the infinity. E is greater than 1. So if I take a number greater than 1 and I raise it to an infinite power, what am I going to get?
Zero. Positive number.
Okay. It is a positive number. The answer to the problem is 0.
Positive.
But what I was looking for is e to infinity is infinity. I just want to make sure everybody recognizes that, which is going to give us 0.
If infinity's in the denominator, it's going to be 0.
But it's going to get a little more complicated. Okay. Limit as x goes to infinity of sine x over the square root of x. Let's think about what is happening for sine x. We looked at that graph last class, right? What does sine do? It oscillates back and forth between plus or minus 1. So my numerator is going to be a number somewhere in between plus or minus 1. Okay, so it's a small number, and we're dividing it by the square root of infinity. Well, square root of infinity is still infinity. Okay, so we get 0. Okay, so this next function is where it starts to get more complicated. However, you guys already know how to do this from college algebra. You just didn't know that it was a limit. When it's a rational function, meaning a polynomial divided by another polynomial, you were told, well, it has to do with the degree of the numerator and the degree of the denominator. But here's where that came from. If we do a direct substitution on this, I'm going to get 2 times infinity minus 1 over infinity plus 1. And now I've got infinity over infinity. So it's not just a question of seeing infinity in the denominator means it goes to 0. In this case, it's not going to. So there's 2 different methods to do this. I picked the less complicated one. If I have $1 million, is one more dollar really that important to me? No. Now, is it really to me? Yes. $1 is very important to me. If I see $1 on the ground and I'm a millionaire, I'm still going to pick it up, right? But in the scheme of things, if I have to tell you what's in my bank account, I'm going to write 1 million as 1 times 10 to the 6. I'm not going to write it as 1, 0, 0, 0, 0, 0, and add the $1 to it, right? And your calculator will only hold a certain amount of digits. So when we're talking about infinity, that minus 1 and that plus 1 are insignificant. Think of it this way. I have 2 pizzas, and I have to share them with 1 million people. Everybody gets none, right? Or I have to share them with 1,000,001 people. Everybody still gets none, correct? So that little 1 there is insignificant. We only care about the terms with the highest exponent. So this looks like the limit as x goes to infinity of 2x over x. Well, x over x goes to 1. So what is this limit going to be? It's 2.
So everything just cancels out.
Those infinities do cancel out in this case. And what you were told back in college algebra about the rules for horizontal asymptotes is that if the degree of the numerator matches the degree of the denominator, you get, so if you had your f of x over g of x was a naught x to the n over b naught x to the n, then your horizontal asymptote would occur at y equals a naught over b naught. And we just made you memorize it. And then there's rules for if they don't have the same degree. So when I look at this one, in 2x plus 5, if we're talking infinity here, that plus 5 doesn't mean anything to me. That plus 1 in the denominator doesn't mean anything to me. So this looks like the limit as x approaches infinity of 2x over 3x squared, which looks like the limit as x approaches infinity of 2 over 3x. So now we're going to get 2 over 3 times infinity. What is this limit equal to? So again, when you were just told to memorize the rules, you were told if the degree of the denominator is greater than the degree of the numerator, the horizontal asymptote occurs at y equals 0. And then you were told a rule for if the degree of the numerator is greater than the degree of the denominator. So what does this one look like? 5 and the 1 are insignificant. 2x cubed over 3x squared simplifies to 2x over 3. If we plug infinity into that, we get 2 times infinity over 3, which is infinity. So this is a limit at infinity that results in an infinite limit. Kind of combined both lessons together there. And if we looked at the graph of this, it would actually kind of look similar to a line with a positive slope. So of course, going off to positive infinity, a line with a positive slope is going to go off to positive infinity. Yeah.
So all these equations are horizontal asymptotes, right?
If it's a finite number, if we get like 2
0, 2, or 5.
or negative 5 or whatever, if it's a finite number, it's a horizontal asymptote. If we get infinity, then we say there are no horizontal asymptotes. Yep.
If you could go back real quick. So from what I'm looking at, can I just like skip all this and look at the exponents for the x and be like, if the bottom exponent, if the bottom has a higher power, then it's going to be infinity.
Yes.
I mean, it's going to be 0.
I'm showing you in painful detail.
We'll just skip all this.
If I was actually, let me. Okay, if we plug infinity into this, whoops, I'm not writing anything. I'm not quite sure what to make of that. I need to deal with the fact that this is a negative exponent. Now I'm going to rewrite this as the limit as x goes to infinity of 1 over 1 plus 1 over e to the x. When I do that, I see that I've got 1 over 1 plus 1 over e to the infinity. So what is happening to that term right there?
0.
It's going to 0, so my actual limit here is 1 over 1 is just 1. So for the next problem, I already rewrote it, so I see it as 1 over e to the x, but now I'm going to negative infinity. So this first one, has a horizontal asymptote at y equals 1. That's when we're going off to the right. That's what the end behavior is. But now when I'm going off to the left, when I put the negative infinity in there, I need to take the reciprocal again to deal with that negative exponent. So this is 1 over 1 plus e to the infinity. And we get 0. So different horizontal asymptote going to the left than from the right. Okay, we already discussed sine x, but the other example I gave you was more complicated than just sine x. If I ask you for the end behavior of sine x, what is it doing as I go off to positive infinity? Do I land on one finite y value ever?
No.
Okay, and the same thing is going to be true of cosine. Same thing is going to be true of tangent. Right? These are periodic functions. They repeat themselves. So they're never going to have a horizontal asymptote that they approach because it's going to keep repeating a pattern and not land on just one y value. Okay? Limit as x goes to negative infinity of x cubed. Now this is one of the parent functions. You're supposed to just kind of remember what it looks like, but college algebra was a long time ago, right? And so if I remember the graph, I know that this is going to go to negative infinity. But if we just plug that negative infinity in, well, if I cube negative infinity, we're still going to get a negative. And if I cube infinity, I just get a bigger number, right? So it's still infinity. So we get an infinite limit for that one. Meaning, there's no horizontal asymptote of the graph of x cubed. Okay, so this one is like the one we discussed a second ago where you said, can I just kind of simplify it all out and figure out what the result is? Well, if you were to show me that's insignificant, and x to the fourth over x to the fourth goes to 1, then what is this limit? What's the answer here? 4. I would understand that. And everything's simplified because it's going to infinity, and so those other terms were insignificant. And once I simplified it, there's no x to plug into, so I can go straight to the ratio of the coefficients, which is what I would have done if I didn't know that horizontal asymptotes were limits. I would have looked at this and said the degree of the numerator is 4, the degree of the denominator is 4, the horizontal asymptote is the coefficients in front of those terms. Yes?
So gives the degrees too for the
Okay,
last
so
two numbers are insignificant.
yes. Okay, so think about this. If I have $100 and I square it, now I have 4 zeros, I have $10,000. But if I have $100 and I raise it to the 4th power, now I have 8 zeros, so I have 100 million, I think. I don't know. But I'm close, right? And so that 10,000 compared to 100 million, insignificant. So we only look at the term with the highest exponent. Okay. The limit as x approaches infinity of natural log of x. We looked at this graph a little bit ago. And it does this. Well, it's going to go to infinity. Now, it doesn't grow as fast as some other functions, certainly not as fast as an exponential, but it is continuing out to the right and up. However, if I wanted to do this as a direct substitution, if I wanted to plug it in there, natural log of infinity is the same thing as saying e to what power equals infinity? Infinity, right? Okay, what about as x goes to negative infinity? Well, think about what we just said about the graph. As x goes to negative infinity, the function doesn't exist there. So technically the limit doesn't exist, but the function doesn't exist there. This is impossible. And think about it. If we plugged in a negative infinity, we're saying e to what power equals negative infinity. Is there any exponent I can raise e to and get a negative number? No. But it's not in the domain, so I simply just cannot do this problem. If you see this problem, it's a trick question. What I can ask, though, is for the one-sided limit as x approaches 0. So if I were to type in ln of 0 into my calculator, what's it going to tell you? Error. And that's because 0 is not in the domain. E to what power equals 0? Not going to happen. So we have to look at the graph and see that as I'm coming from the right towards 0, what is the graph doing? It has a vertical asymptote at x equals 0 that is approaching negative infinity. All right, so tell me about this one. If I plug in infinity what do I get? 5 plus 0 plus 0, because both of these are going to 0. Now this next one is trickier than you might think. First of all, that plus 1 is insignificant, right? And here's why it's tricky. That makes me want to say the square root of x squared is just x, and x divided by x is 1. But we don't want to do that. What happens if I plug in negative infinity over the square root of negative infinity squared? My denominator is going to become positive infinity. Right? When I square that negative, I get a positive infinity that I then take the square root of, and I'm going to get negative infinity over positive infinity is negative 1.
What if the radical get rid of the exponent?
It does,
Then how is it positive?
because you don't want to simplify before you plug in. Let me... Okay, so in everything we've done, we've been finding vertical asymptotes. Those are our infinite limits. We found horizontal asymptotes. Those are our limits at infinity. So I can give you a function and ask you to find those for me. So if I start with the horizontal asymptotes, let's rewrite this. So that I can see the highest exponent. Then for my horizontal asymptotes, they're going to occur at the limit as x goes to infinity of x to the fourth plus 8 over negative x to the fourth plus x squared. We're going to say the 8 and the x squared are insignificant. So we're going to get negative 1. So we have a horizontal asymptote at y equals negative 1. Now, we have to check going to the left as well. So the limit as x goes to negative infinity nothing's going to change, right? I don't have that special case. So I can simplify this and say that it's also going to negative 1. So if I were to look at this on a graph, I would see that going off to the right and going off to the left, there's going to be a horizontal asymptote in both directions at the line y equals negative 1. Okay, now vertical asymptotes occur when the denominator equals 0 and are not removable, right? Okay, so I'm going to pull out, I can't factor the numerator, right? That's like when we had one earlier that was an x squared plus a number. Since it's a plus, it's not a difference in squares. I can't do anything with the numerator, but in the denominator, I can factor out a negative x squared. And that'll leave me with x squared minus 1. I factored out the negative because I didn't want to have a leading coefficient that was negative for the x squared minus 1 because I still need to factor that. So this is x to the fourth plus 8 over negative x squared times x plus 1 times x minus 1. None of those is going to cancel with anything in the numerator. So we're going to have vertical asymptotes from here. If I set that equal to 0, I get a vertical asymptote at x equals 0. From here, I'll get a vertical asymptote at x equals -1. And from here, I get a vertical asymptote at x equals 1.